Okay, today we will have two presentations. The first presentation is given by Ruofan, and so I think this topic is very related to Ruofan's undergraduate major. So that is about statistic testing. So when we are doing experiment, usually statistic testing is a very important mathematical tool for us to confidently saying that one approach is better than another, or kind of subjects is more adapted to one approach compared to other subjects. So Ruofan will introduce such a mathematical tool. I think that will be very useful for all the PhD students or the student who is willing to take an academic job. The second presentation was given by Yihao. So it will just report the most state of the art, so the latest state of the art approach about how to generate comments. Okay, Ruofan, will you please start?
Hi, good afternoon, everyone. So today I'll present a tutorial on hypothesis testing. In this tutorial, I will summarize some popular statistical testing methods, t-test, Mann-Whitney, and I think I will not cover ANOVA because it's less commonly used in computer science subject. ANOVA is more commonly used in biology or chemistry when we have many experiment groups and control groups. So t-test and Mann-Whitney are used to compare two distributions. So we want to test whether these two distributions are the same or not. First, I want to point out the difference between random variable and realization of random variable. So we use capital letter to denote a random variable. Random variable tends to follow certain distribution. Either we know the distribution's parameter or we don't know the parameter inside the distribution. An example would be if we roll a die and observe the outcome. And we know that the outcome has in total 6 possibilities, and each outcome has equal probability to come out. So the outcome is a random value, and it is described by the probability mass function. A probability mass function is just the probability of x equal to I is 1 over 6, where I is from 1 to 6. In contrast, what is the realization of random variable? It is we literally roll the die and get several observations because those observations has already happened in the past and they are already observed. So once they are observed, they are no longer random. The value is fixed. So the small x1, x2 are realization. So they are just numbers. They are not variables. Okay.
Please go on.
Now I shall introduce the concept of hypothesis testing. A statistical hypothesis is to use observed value, which is the realization value from a random variable to test an unknown parameter. And this unknown parameter is the parameter inside the random variable's distribution. For example, we can have a random variable, which is the height of a 20-year-old adult. This x is a random variable because it is different if we measure a different adult. A legitimate assumption is that my x follows a normal distribution with a population mean mu and population variance sigma square. But we don't know mu and sigma square because it is impossible to measure all the heights. So now we want to test a hypothesis about mu. For example, I can propose some guess. I guess that my mu maybe is 1.6. Then now I want to verify whether my guess is likely to be true or not based on some observations from the populations. Suppose we have n observations x1 up to xn. So these are just some numbers, some realizations. A very crude verification is that we just compare x bar with 1.6. If x bar is close to 1.6, then we think our guess is maybe reasonable. Otherwise, we just reject our guess. We think mu is not equal to 1.6. But we need some formal test statistic that can provide a high confidence to reject or accept our guess, instead of simply taking the difference between x bar and 1.6.
I have a question here. So when you say we know there are normal distribution, and I also know there's some other like student t distribution. When you said it's unknown, do you refer to we don't know what type of the distribution it is, or simply if we assume it's a normal distribution and we don't know the mean and
we don't know the parameter, but we know the type of distribution.
It's normal distribution, right?
Yeah.
Okay.
Yeah, I think a lot of statistics testings have the assumption of distribution. For example, the t-test statistics can only apply on the normal distribution. Otherwise, it is not applicable, theoretically speaking.
So in hypothesis testing, we have a notation of H0 and H1. So H0 is just our guess. Our guess is mu equal to 1.6, then H0 is just this equality. Then we let H1 to be all the alternatives. So H1 will cover all the rest cases we are not interested. And our goal is to test how big the difference between x bar and 1.6, right? Instead of using simply x bar minus 1.6, a better statistic is normalized by the standard deviation of random variable x bar. For example, I have a set of observation x1 up to xn. Then from this pool of data, I can estimate an x bar. But if I sample another n observations from the population, then I will have another estimate for x bar. So I can do this repeatedly. Then we'll have a different x bar. If I observe that my x bar fluctuates a lot from data to data, that means if I observe I have a really high difference between x bar minus 1.6, maybe just out of luck. So the standard deviation here describes the reliability. Like if my x bar is close or very far from 1. Should be if x bar is very far from 1.6, but x bar is not stable, then we believe the test statistic is still small.
So that means we need to sample a lot of times for x bar. So we have a set of observed x bar.
Because for x bar, recall that we assume that my x follows normal, so x bar also follows normal, so it can be computed. It has a formula to compute it.
Okay.
But if we do not have normal assumption, then we need to use some method to estimate the standard deviation of x bar. And the method we use is called bootstrap. Bootstrap, if you are interested, you can search about this method.
Okay. Sure. So here it's very clear. The takeaway is that we should not using the x bar, we cannot simply compare the x bar and 1.6. Instead, we should repetitively sample a subset of x and got a list of x bar, and we compare the standard x bar. So I have a small questions here. So this x bar is a single x bar, and this x bar is a set of x bar. Yeah, it's capital the x bar, and so since we have a list of x bar, and then which x bar do we use in the numerator?
When you have a set of x bar, then you can just compute their variance.
Okay, so yes, we do compare the variance, but you mean that a better statistics is from the numerator, it is x bar minus 1.6. So which x bar do we use since we have a set of x bar?
This is the observed X bar.
Yeah, but we have a lot of observation, right? So suppose there's well, I'm not sure whether I understand it correctly. So this is the this is the unit. This is the all x. This is all the x. Let's say the x to be u, and we sampled for multiple times. So this is big X bar one.
So here we only sample for one time and get a small X bar. Because we assume normal, so this can be computed from only one pool of observation. So we don't need to sample all the time, sample many times to get different X bar.
Yeah. So I get a point. So you sample once, you get an X bar.
Yeah.
And then you are also you're going to estimate the standard deviation of X bar with the distribution or with the standard deviations in X bar one. Is that the point?
Yeah.
Okay, I got it.
So let's see what we have now. We have the hypothesis, we have the testing statistic. Now we're only left with the threshold. If the absolute value of my test statistic is larger than the threshold, then I will reject my H0. So I believe the population mean is not 1.6. Otherwise, I think the population mean maybe is roughly around 1.6. But then how to decide the threshold? Like what I mentioned, because my X all follows normal, so X bar also follows normal. So X bar minus mu divided by standard deviation of X bar is standard normal.
Okay.
But here, so here you see there's an explicit formula to estimate the standard deviation of X bar. So we don't need to sample many subsets, then compute many X bar. So actually we can estimate this based on only one X bar.
Okay, please go on.
But this parameter is population variance, so we don't know. So we still need to estimate from our samples. But when we estimate this sigma square from samples, it becomes sigma hat square. Then this test statistic no longer follows normal distribution. Instead, it will follow a t distribution. So that's the link between normal assumption and t distribution.
So what's the, sorry, I somehow forgot the concept. What's the distribution of t distribution? The definition of t distribution.
T distribution looks very similar to normal. So suppose this is normal. Then my t distribution would be somehow fatter than normal. We can understand in this way.
Is there a formula for the t distribution? I somehow forgot it.
Yeah, I think so. Yeah.
So it's the shape is very much looks like a. So suppose you have an estimations. So, but the t distribution cannot be changed by change the normal distribution by, or change the form of the distribution by with its parameters altered. I mean, given the t distribution, there must be a form. Maybe you can keep going on.
Oh yeah, I think there's a PDF for t distribution.
You will follow up with such an introduction?
No, I didn't put the formula inside.
Okay, but
that is not very important because you can imagine t distribution is just a scale version of normal distribution. It's just fatter than the normal distribution.
So sorry to interrupt again, but I have a question from last slide. When you said we only sample X bar for once, I didn't quite follow. Didn't
Yeah, you should raise these questions.
Sorry.
Because you have N realization, right?
Mm.
So then you just compute X bar and you only have a single X bar. That's the
Yeah.
X bar you use here.
Then what about standard deviation of X bar?
Standard deviation is now X bar is a random variable instead of single observation.
Yeah, I think
So is it?
let me explain a little bit. You can correct me if I have some wrong, incorrect understanding. So by right, we supposed to, if we would like to have a standard deviation of the, because this red X bar is a set of data instead of single, and it is supposed to be a set that have X bar 1, X bar 2, and X bars n, right? So
actually X bar is a random variable follow distribution of normal.
yeah, I got it. I got it.
You won't have a set.
Yeah, so that is what I going to explain. So by right, if we do not know the distribution of X bar, we have to sample a lot of times so that we compute the standard distribution or standard deviation. However, since the distribution of X is assumed or is fixed, so X bar is also for the distribution. It also for its distribution, but with its standard deviation changed or reduced. So we do not need to resample so many times. We can just estimate. We just need to estimate the standard deviation X bar through the induction. Have I made myself understood?
So this slide is trying to estimate the standard deviation of X bar.
Yeah, so we do not need to repetitively sample X bar. We just need to sample X bar once, or we just need to have sampled once. Do not need to repetitively sample a set of X bar.
Use those realization of X to estimate X bar. Oh.
Yeah. So no need to sample again.
Okay. Thank you.
Yeah, so because standard deviation of capital X bar has an explicit formula, so which can be estimated by our realization.
Yeah, I think it's very necessary to recap those foundations. So sometimes we believe some concepts we are fairly clear, but when we really try to explain or use it, there's still some fuzzy and confusion there. And that is goal of these Ruofan's more basic but a more fundamental presentation.
Once we know what kind of distribution my test statistic follows, then the things becomes easier because I can set my threshold based on the quantile of my distribution. So this notation means suppose this is my t distribution, and this is the value of t 0.025. Then the area on the right-hand side is equal to 0.025.
But how do we calculate t 0.025?
Like you can call a function because t distribution has a probability density function, right? So from the probability density function, we can compute the cumulative density function. Once we get the cumulative density function, we can get the inverse function of cumulative density function. So given a quantile we want, we can map it to a
value. Okay. So is there any questions here? I think Ruofan has explained it well, but I hope some of you can still follow up. Otherwise, we lose the meanings of this knowledge dissemination. So can you have a question here? Maybe you can test whether everyone follow your point. maybe let me say. So given the threshold of 0.05, so even given the threshold 0.025, what is the probability of H0 is unreliable? So maybe I can use
reject H0.
Yeah, no. So here,
reject 0.
yeah. So here, so even if we, how does, so, yeah, even if we reject H0 or believe in HC, oh no, sorry. My point is that, how do I say that? My point is that even if we reject even if we reject H0, what is the probability of its reliability?
Huh?
Have I made myself include?
So do you mean that if given that H0 is true, what is the probability of reject H0?
Yeah. So somehow this is the point. So maybe Xiangling will have a try.
Let me think about if.
So when we set a threshold of t 0.025, so when, for example, if this value is larger than t 0.025, so somehow we can reject H0, right? So
Yeah.
and we can reject H0, and even if we reject H0, there's still a probability. We still have a probability that it is not that reliable. So what is its probability? Giving t is 0.025, and so somehow this is a probability, this conditional probability there. I'm not sure. I'm not expert in statistics. Actually, Ruofan is. So if I do not phrase myself well, Ruofan, you can help me rephrase.
Yeah. I got your point. So, from my understanding, you have 0.05 chance to reject H0. But I don't know what's the probability of H0 is true. So I know the rejection, the probability of reject is 0.05.
Yeah, actually this is just 0.05 because when we are doing the test, we assume that the population mean is 1.6. So when we are doing the test, we actually have this condition inside.
Yeah. So, but my question here isn't if we're choosing the probability of 0 to 0.7, so the shape is symmetry, right?
Yeah.
So if we're choosing 0.025 there's supposed to another 0.025.
So it's 0.05.
So when they add them together, isn't that should we sum up them together as 0.05?
Yeah.
So
I assume the probability is 0.05. Am I correct?
Yeah, correct.
But why do you have the condition that H0 is true?
Oh, because this probability is just when we wrongly reject H0. So I just want to make it clear that there's a condition here.
Yeah, okay.
So what if we choosing the value of t equals 0.005? It's still possible, right?
Yeah. Then your rejection region becomes like this. Then your rejection is smaller.
And the probability is 0.01, right? Okay. Okay, I think.
So
please.
So the interpretation here is that assume my real population mean is 1.6. But if the test statistic is too large or too low, they will believe the observed data is unlikely to come from a distribution with mean of 1.6. Thus, 1.6 may not be a good guess for population mean. Hmm. So the above test is called t-test. In fact, a more general case is when we test mu is equal to a specific number a. In the previous example, a is equal to 1.6, but actually it can be any number we want to test. And then we reject h null if my absolute value of t is larger than some quantile. This quantile is called critical value.
Please go on.
Okay. And you may also have seen the term significance level in the hypothesis testing. It's actually just the area above critical value. It's just what we're talking about, the conditional probability given h null is true, but we wrongly reject h null. So here, if we set the threshold to be 0.025 quantile, and by symmetry, we have two areas on the left-hand side and right-hand side. Then we are testing at 5% significance level. Of course, we can increase the threshold to be a quantile of 0.005. But if we increase, that means I move my critical value further to the two tails. Then I really need a high value to reject h null.
So it's not that friendly to researchers, but it's maybe more, we can have a more confident in practice. So for Aaron, is Aaron there? Hello, Aaron. So Aaron, okay. So when we are working the experiment with Chen Yan, so we still, so nowadays we are automatically generating the test cases. So when we're using two approach one and approach two. Approach one we call it A1, approach two we call it A2. So we run it for maybe 10 times. So maybe the first time the coverage is 0.9 and 0.8, whatever it is. And the next time is for approach two, the coverage may be 0.88, 0.7, 0.6, etc. So we compare the average, right? So this is the approach we're doing. So we have XA bar and an A2 bar, right? So this is what we're going to compare whether A1 bar is larger than A2 bar or vice versa. But a more strict idea is that we not only compare the average, but also compare the statistic because we have a set of the data. We're going to count whether A1, the coverage of A1 is statistically significant than A2. So only by this we can have a more confidence saying that for a method MM, so the approach of A1 is statistically better than A2. If the average of A1 bar, if the average A1 bar is larger than average A2 bar. Right, so this is the final goal. So when we are doing empirical studies, we're not only looking to the average. If we want like to say method A, if suppose we have approach, if we want to select a set of methods where A1 can be steadily better than A2, we're not only looking to the average because sometimes average is so biased. The average is so biased. We only looking to we combine average with statistics, and moreover, when we are using the static values, the norm is using 0.05, right? So here is a 0.5% of this 2.5%, and here is a 2.5%. So for p-value, we usually use 0.05 the p-values. But if we select examples, we will go to some extreme. We're using the p-value of 0.005 so that we can make for more obvious examples to see which method, what kind of method where A1 have a more obvious advantage over A2. So that is examples for how we apply statistic testings in the research in software, in the research of software testing. Okay, so keep going on. Sorry for interruption.
In previous section, I'm talking about one sample test. That is, we only have one group of observation and we want to test whether the mean is equal to some number. But sometimes we want to compare two groups of observations like the project you mentioned just now. For example, I have a treatment group. I developed some drug and I want to test the effect of drug. And I have a treatment group and control group that measure whether there's a significant difference between the two groups.
So I think sometimes we also call experimental group and a control group. Right? It's just about the terminology.
So there are two types of two-sample tests. The first one is called independent two-sample test. That means the two groups are from different individuals. The second type is called paired two-sample test. That is when two groups are related. For example, the first group is a set of patients before treatment, and the second group is the same set of patients after treatment. So because the individuals from group 1 and group 2 are the same, so these two groups are related.
So you are giving a definition of independent independent groups, right? So examples are related patients. Okay. So maybe I still would like to ask. Maybe this time I ask Yufan. So hello, Yufan. Hi, Yufan. Is Yufan there?
Yeah. Hello.
Yeah. So have you ever taken the course of the statistics? I think you definitely take the course of the probability. So I think you still take the course of the statistics, right?
Yeah. I did took the course of random random processing. So I learned a bit about students test, but I almost forget it now.
Yeah. So here we have a definition of independent samples. So can you raise another example? Or can you raise it? Giving this definition, can you think about examples in our real world for some independent samples?
Independent sample. Maybe maybe like I want average of maybe I play cards. There are 1, 2, 3, 4, 5, 6, and 6 cards, and I just pick only one every time. And I thought the average of the number will be 3.5, but maybe I have tested many times. The result is 3.4.
You mean test another time, so you want you get an average. So it's you mean a card is more like a dice, right? Your example is more like a dice, right?
Yeah,
Dice, it have a random variable distributed around 1 to 6. So what you mentioned is that you throw the dice for different times. For example, we're giving two tests. Each test will throw the dice for n times. And for the first time, you get the average number of 3.5. And the second time, you got an average of 4.5, right? And also, you repeat the experiment again. You are saying that maybe this is group 1 and this is group 2. So you are saying that for this experiment, this group 1 and group 2 are independent. Is that your claim?
Yeah. And I think maybe through our experience or the statistic experience, we thought the average should be 3.5 because every number is equal probability. One maybe all is 1/6 probability. So the average maybe should be 3.5, but our experiment result maybe not 3.5.
So here, let's get back to the definition of independent group. So Ruofan, so can you give your answer? So do you think given the same dice, we have group 1 and group 2. Maybe this group 1 and group 2 means we have different way to throw the dice. So the first group will have the average number of 3.5, and the second will be 4.5. Actually, the number doesn't matter. Do you think these two groups are independent groups?
No, they are not independent. But kind of what you want to test here. Because I didn't
We
say.
test. I'm just saying that we generate group 1 with a method of with the throw we're tossing method 1, and we generate group 2 as a tossing method 2. So I'm asking. So the question is asking, are group 1 and group 2 are dependent groups or independent group?
I think they are not two sample tests. Because in two sample tests, we want to compare two distributions, whether the two distributions are the same or not. So it is not relevant to the problem I'm talking about here.
So here you're saying the two sample test is just going to test whether they are of the same distribution or not.
For example, I have a drug, okay, and then I use it in my experiment group. But for my control group, I may maybe give them a placebo. Then I measure the blood sugar level in control group, denoted as X, and measure the blood sugar level in the experiment group, denoted as Y. And I want to test whether the mean from group 1 is equal to the mean of group 2. So I'm actually testing two distributions. I'm testing two groups.
Two groups, okay.
Yeah.
Yeah, we tested.
Maybe I
for
can.
what? Okay, please go on.
No, I only want to say maybe I can raise a more simpler example. Like you measure the height of different ages, like from age 0 to age 10, and the age from age 10 to age 20, and above age 20. So like the height would be independent groups.
Yeah, definitely. So we are actually talking about the definition of independent group and dependent groups. So let's get along, forgot about the distributions. We just, for example, we are giving examples. We are going to judge whether these examples conform to the definition of dependent group or independent group. That's all.
So if there's two dice, one I just randomly experiment two dice, so the result will be
independent.
Yeah.
And if it's the same dice.
Okay, if the same dice is not independent.
It's dependent. It's correlated. So that's all what I want to say. So I don't understand what Ruofan means irrelevant or not relevant. I think the problem definition is quite clear here.
Because I'm talking about two sample tests, so you can say that if you have one die, it is related, but it is not a two sample test, right? It is essentially we are not trying to compare.
And what is the definition of two sample test?
We want to compare two groups of two distributions. Suppose we have two distributions.
Yeah, we have. Yeah, so we.
I want to know whether they are the same or not. Yeah,
so we have group 1 and group 2. We want to have they may have different distributions. We want to test whether they're same or not.
But you have the same die. If you have the same die, why you want to test it? If you have two dice, then you can compare. But you only have one die.
Have one die, but
if you have one die, then the distribution is just the same.
No, not necessarily. Maybe I throw the die with different tossing, with different tossing approach. For example, I still using random throwing, so it may form the uniform distribution. Another way, maybe I'm a very skilled gambler. I toss and throw the die in a very different way.
Then if you throw in a different way, actually you are using two different kinds of dice, right? One is fair, the other one is not fair.
Yeah, so I'm just talking about such a way, and I think that form conform to definition of two sample tests now. Am I right?
So if the group 1, the result of group 1 and the result of group 2 is different, like the 3.5 or 4.5, then can we say they are different?
Group.
Oh, we need to like what we do before, we need to have some test statistic to
Yeah, so here the
confirm.
question is whether
Yeah.
group 1 and group 2 are two sample tests.
Yeah, if the two dyes are different, then it's two samples.
Whatever. So if the dye is the same dye, but we got the groups, we got the samples in different dosing technique. So we got a group 1 and group 2. So in this case, group 1 and group 2, can those two groups conform to definition of two sample test?
Yeah.
Okay.
Okay. Thank you.
Then they are related, right? It should be.
Yeah.
But if you are using different dosing technique, then you assume they're independent, I think.
But I think giving your examples, if the dye becomes patient, right, becomes patient, and the dosing technique becomes different treating method, isn't it all of the same similar? The problem becomes similar. In this case, do you think G1 and G2 are dependent or independent? The same group of patient, but we treat them in different way, so we get result of G1 and G2. And the next question, and the previous question is that given the same dice, and we throw the dice in different way, so we get a G1 and a G2. So you think the first problem is?
Because if you change the dosing technique, then you actually change the quality of the dye, change the essential quality of the dye.
And if we're giving the same patient, we're using.
Can we just forget about this dye example? I think it's a little bit
just here, just
strange.
it's just a thinking experiment. We would like to get the definition very clear so we can keep going on.
Because
anyway,
because usually the pair to sample test is only used when we have a certain kind of treatment. So
treatment.
Yeah.
The treatment means that giving just like the example in next slide.
Yeah.
So the same group patients, and we will like test its blood sugar level. One is control group that we're giving some.
Placebo.
So yeah, placebo. So placebo means that we're giving some medicine, but this medicine essentially does not have any effect. But another group of the same group of patient, right? The same group patient, and then
No, this is independent. This is independent.
Oh,
so
sorry.
This should be another group.
So there's another group of patients.
Yeah.
There's another group of patients. We feed them into a medicine which is supposed to take effective, and we compare these two groups to see whether there's a difference between their sugar levels. Yeah. I think we can forgot those examples, but anyway, so if we forgot these examples, there's still a question left for a definition. So anyway, I think our discussions make our more close to the truth of the definition of one sample test, two sample test, and independent two sample test, and the dependent sample test. Okay, let's keep going on.
First, let's look at independent two-sample test. If we assume the data follows normal distribution, then we can use t-test. Otherwise, if we do not put any assumption, then we can use Mann-Whitney U-test.
So this is a major test that we're going to introduce today, right?
So the two-sample t-test is very similar to one-sample t-test. But I want to test the mean from group 1 is the same as the mean from group 2. If their mean equal, then I believe the drug has no effect.
We don't consider their variance and standard deviation. It's supposed to still consider not only. I think mu is necessary but not insufficient condition. Am I right?
Yeah.
Okay. So the first hypothesis is going to test the mu, and will we also test the variance here? The variance here.
You want to test whether the variance equal or not?
Yeah. Suppose. Maybe I stop interrupting and let it finish.
So t-test will not test whether the variance equal or not.
Mm.
So it's just to compare the mean. Because I think the inherent assumption for t-test is that if their mean equal, then the distribution is almost the same.
Mm. That assumption does not sound hold true in practice.
I think it's a simplification. So instead of testing the whole distribution, I'm only testing the mean.
I think the standard deviation or the variance have been taken consideration here. So that's why I'm saying I'm not going to interrupting you anymore and let you keep going on.
I have a question in terms of terminology here. So in the last line, the Tn plus m minus 2, what does the n plus minus 2 mean?
N is the number of example in X. M is the number of example in Y. And this Mn plus n minus 2 is the parameter for the T distribution. So it's the degree of freedom for the T distribution.
Degree. Oh, okay.
So if we have different degree of freedom, then the distribution will have different shape.
Oh, so this is the only parameter in the formula of
So T distribution have only one parameter.
Yeah, because T distribution is centered at 0.
So can you quickly using Wikipedia to show us the formula or the distribution formula of the T distribution? So not only you but also me need to recap of the foundation. Yes, as you said, it's really the T is considered including the parameters of.
Oh, this is the PDF. Looks very complicated.
Yeah. So and then simplified the explanation.
The V is
degree of freedom.
V, so T is fixed value.
T is the
T is just
variable.
Yeah, T is a variable here.
So V is a parameter.
Yeah.
V is the degree of freedom.
So we can say when V takes different values, it looks different.
Okay.
So if V becomes larger, then it will become more flat, right?
More flat, yeah.
Flattened
will be flattened since.
Oh, then flattened. Okay.
I think Xiaoling is supposed to be familiar with T distribution because your dimensionality reductions in high dimensions. It's a high dimension is called what distribution? Normal distribution? Not normal. It's kind of normal distribution. And for the low level,
it's supposed to be student T distribution. I don't know the difference between.
It's the same.
It's the same. Oh, okay. Oh.
So the patient in the control group and the patient in the experiment group is different.
Different.
Independent.
It's independent, yeah.
So now we want to show the effect of the medicine. So we want to check the distribution of the two groups. Okay.
And also the
so it's a,
please go on.
So the goal here is so H1 means H1 means the drug tax effect.
So only compare the median.
No, so it's
median
here the hypothesis. So you can see the fourth line. The fourth line, we're going to construct another random variable.
Okay.
By x bar minus y bar.
Okay.
So and this x bar minus y bar is just like the x bar we say in one sample t-test. So we want to have a normal variable to test, then convert it to a t-test statistic.
Let me think about it. So here, the um, so x bar, y bar is
Random variable.
okay, the random variables.
Mm.
So that means as long as we form the but
Oh,
this is the form.
sorry. This is small x bar. This is small x bar.
Mm,
This is small y bar.
okay.
This is small.
Okay, we understand.
Mm.
So the rule is that as long as a random variable conforming to as long as a variable conforms to the normal distributions, we can use the t test statistics to do the job.
Yeah.
So maybe I should have the same request as Xiangling. Can you go back to a few slides here? Previous one, still previous one, even previous one, previous one, previous one. Yeah, here. So here is here. Maybe I just skip these ones or did not focus on this one. So as long as the random variable conforms the normal distribution. So here we are. The rule is that this one have to follow t distribution. So that is a rule, right? And this one, suppose it's normal, and this one is standard normals, and giving the variance is sampled. So okay, so it's more like t distribution is an estimation or estimated normal distribution. And I have such an impression or intuition. So when the variance is the actual variance, it becomes a normal distribution.
Yeah.
Otherwise, it becomes a t distribution. As long as it forms two distributions, we are using another kind of the formula to represent it, and we can using a specific threshold to define the quantile. So that is the idea. Okay, thank you.
Sorry, can you repeat yourself?
Okay, so for example, so as long as a variable forms the normal distribution, so by right we should be using normal distribution, right? But in actual, this sigma we can never know the real sigma it is. So we have to use an empirically estimated sigma. So it will become sigma hat. As long as this sigma becomes sigma hat, so this one does not follow the normal distribution anymore, according some kind of rule, but I don't know what rule exactly it is. So we call these variables follows t distribution. So that becomes a rule. So as long as these random variables follows t distributions, we use another formula. I think use the formula of t distributions. As long as we given the t distributions, as long as we set a quantile of t, when set t is here, the quantile is supposed to 0.025 quantile because this is a symmetric, because this and also giving the t distribution must be an estimated normal distribution in practice. It must have the similar shape of normal distribution, and this function or formula is supposed to be symmetric. So as long as we set a quantile 0.025, and there must be a symmetric quantile as another 0.05 on the other side. So we sum up the area together. So as long as the hypothesis is supposed to be true, or we can as long as we can reject the hypothesis H0, or as long as we reject H0, it means that we can have a probability of 0.95 or the 95% of the confidence to saying that we can our hypothesis we can reject the H0. Somehow that is the idea.
Okay, yeah.
Okay, so maybe we can recap these or keep talking this offline. and Ruofan has already taken almost an hour. Let's keep going.
Okay,
I
so
suppose to ask less questions later. We still have Yihao to present. Need to present, yeah.
So now just like in one sample test, we have x bar follows certain normal distribution. Now my x bar minus y bar follows normal distribution. And essentially, I'm just testing whether it is equal to 0 or not. So yeah, I can establish the t-test statistic and test against the quantile of t distribution. But here my t distribution will have different parameter. So all kinds of t-tests, either it's one sample t-test or two sample t-tests, require assumption on normal distribution. But what if we don't put any assumption on x and y? So if x is from a distribution f and y is from a distribution j, and we want to test the null hypothesis that f is roughly equal to j, we can use Mann-Whitney test. The step one of Mann-Whitney test is that I collect all the samples from x and y together. Then I get a pooled sample of x and y, and I sort them. When I sort them, I can get rank for each example. Then I define Tx to be sum of the rank for all examples coming from x, and Ty to be sum of rank for all examples coming from y. If f and j are close, or we pool x, y, and y together and rank them, then the rank sum for x and y should be close. So for example, I have some realization of x and some realization of y, and we sort them. It's easy to observe that distribution of x is very different from y, because all realization of x is a head from realization of y. So I can compute Tx. First, the rank of each item is 1, 2, 3, 4, 5. From up to 10. Then I just sum all the rank for realization coming from x and all the rank for realization coming from y. And you see Tx and Ty are really different. So that verify our intuition is that if f and g are close, then Tx, Ty should also be close. I have a question here. Can someone help me to compute Tx and Ty in this case?
So anyone want to volunteer? If no volunteer, maybe I can then assign someone. So let me see. Now Xiangling and Yufan are working. How about Yihao? Yihao, are you listening? Or are you still following the? Hello, Yihao. Yihao is not following. Aaron, is Aaron there? Aaron, hello, Nima.
Yes.
Yeah, are you still following our discussion?
I can't answer the question.
Okay, so Ruofan, would you please repeat the questions for Nima?
Nima, do you understand Tx and Ty here?
Not really.
So suppose we have two groups, right, x and y. Then I just pull them all together and rank them. When I rank them, I can compute the rank for each example, right? So Tx is just I sum all the rank for observation from x. Ty is just I sum all the rank for all the yi values. So for example, we have green ball and orange balls. So I put them together and sort them. And when I sort them, I can get the rank, right? So we can compute Tx. Tx is basically the rank for all the green balls. Ty is the rank sum for all the orange balls.
Okay.
So yeah.
So here, if we
You can
compute Tx,
label. You can label the number. For example, what is Zx, Zxi, Zxi, Zx1, Zx2, and what is Zy1, Zy2, and we can compute the sum of them, right? The ranking.
So, okay. Oh, yes. So we would need to add the rank of this one, etc. So it would be like it starts from 1, like 1 plus 3 plus 5, etc.
Yeah.
Oh, yeah. Okay, thank you. Okay, thank you.
Thanks.
Okay.
Oh, okay.
The great answer.
Yeah.
Yeah.
So
yeah. It's impressive. You didn't listen, but you get a good answer.
So you can see that now it seems the distribution for X and Y are roughly the same because they're shuffling together and they get, yeah.
And also that given us an assumption of Mann-Whitney. So the size of X and Y is supposed to comparable, right? Right. So otherwise, even if the numbers in X is very, very small, but X have a very large size, and this matrix does not work anymore.
But I have a question here. So if the ranks are roughly the same, then I think it can only tell that they are from probably the same distribution, but Y is normal distribution. What about other kind of like T distribution?
When we do Mann-Whitney, we do not assume normal.
Yes, that's the case.
Yes, so you can only tell that they are from the same distribution.
Also, you cannot tell what type of distribution.
Yeah.
Yeah. Yeah, but that's not our focus.
There's no focus. I think Xiaoling, you still you may need to clarify the goal. The goal is that whether X is significantly better than Y, or or whether the difference between X and Y are statistically different. As long as we can know this point, then our question or the ultimate goal is addressed. So according to but if we have the distribution, we have a very beautiful mathematical estimation of the probability, right? But now, what if the state samples is not normal? If it is normal, so we provide such a ranking-based approach, which is called the Mann-Whitney U-test, to do the trick.
So because Tx plus Ty is fixed, Y is fixed because it's just the sum of rank for all the examples. So we can look at either Tx or Ty. It's just equivalent. We will reject each null if either Tx or Ty is too small or too large. So we'll reject each null when the minimum of Tx, Ty is smaller than certain threshold. In practice, the test statistic is not directly Tx and Ty, but some transformation of Tx and Ty. But the idea is still the same. If F and J are close, then Tx, Ty are close. There's actually a table for Mann-Whitney test to check the threshold when you use different M and N. So yeah, you don't need to calculate.
So that's supposed to be so my statement is incorrect. So if Tx and Ty is not of the same size, so the Mann-Whitney still apply. Right? M is the size of T. The M is the size of X. N is the size of Y. And if the size of X and Y are very, very different, so we can still apply Mann-Whitney.
We can't.
We can't. So, but here, but here, so here comes that if H0, if either, is this either supposed to either Tx or Ty is too small, too large? And so too small, too large means that xy, tx and ty are very, very, and one of them are very, very small, and either of one of them is very large. And there's also m, and there's m, and there's n there. So in that case, it means that the size can be different.
Can be different, but cannot be too different, right?
But here it is too different according to your second bullet. We just rejected it.
If it is too different, then the smallest value of tx, ty will be very small.
Yeah.
It will be very small, then we'll always reject H0. So we always believe they are not coming from the same distribution.
Always believe they're not statistically different. But anyway, it would be not a concern of the size, because in the majority of cases, the two samples should have the same, the x and y is supposed to have the same size or exactly the same size. That is in the majority of the cases.
Now I finished introducing the independent two-sample test. So now we can talk about paired two-sample t-test. For paired two-sample t-test, we also have two cases. The first one is normal assumption. Second one is without normal assumption. For the normal assumption case, we can use a t-test called paired t-test. Suppose we have measurement of blood clotting for 6 individuals before and after smoking. So when you say there's an ID rule, for patient ID equal to 1, these two observations are coming from the same patient, before smoking and after smoking. And we would like to still test the hypothesis mu x equal to mu y. But we cannot do independent two-sample t-test because xi and yi are from the same individual. What we can do is that we can transform xi, yi to be di equal to xi, yi, and test di instead. So we are testing the difference, whether the mu of d is equal to 0 or not, whether the difference is 0 or not. And d-bar, because d-bar also follows normal, so we can use the t-test.
So will you please go back to how about the, sorry, I kind of forgot, how about the independent t-test looks like?
For independent t-test, we do x bar minus y bar.
X bar or x bar minus y, x y bar. Okay.
But for paired, we first compute the difference. Then we test d. So d is our new random variable we introduce.
That is reasonable.
If we don't have assumption on the what kind of distribution x and y follows, then we can still use a rank test. And for paired two-sample test, the rank test is not called Mann-Whitney, but it's called signed rank. But the idea is just very similar. If smoking does not affect blood clotting, then we should expect the DI. So DI is equal to before treatment minus after, before smoking minus after smoking, and minus DI. Minus DI is after smoking minus before smoking to be identically distributed. Because smoking has no effect, so DI and minus DI should be roughly the same.
So that means we need to have 2 samples. I mean experiment twice. Just for example, we get the blood for the blood clotting levels. So we can have L1. So we somehow the first experiment is that before smoking and after smoking, we test them twice, and then we test the blood set before smoking, after smoking, and this is YI means blood after
smoking.
So how can they not identically distributed?
When, for example, when after smoking, my blood clotting level significantly increase, then I should expect that my DI will be negative, negative, but
here,
minus DI will be positive.
We had 2 actions. The first is not smoking, is smoking, and not smoking. Right, there are 2 data set. So suppose the 30s, and after smoking.
Oh, why there are 2 data sets? No, there are still. Why there are 2 data sets?
I mean, so here the smoking behavior, right? The smoking. So if you what I mean is that so suppose smoking have a very good effect. So if when it's not smoking, the blood clotting supposed to have a value of 30s, and after get a 50s. So after smoking, it's supposed to be back to normal, should be 30, and instead of be 60 or 30.
Wait.
There will be a
no. We don't have the third column. We don't have the third column. The xi here is just the xi here.
If that's the case, how could it be not identically distributed?
For example, if smoking can increase the blood clotting level, then I should expect that my DI to have many negative values, right? Negative. But my minus BI will have many positive values, right?
Oh, the point is that this is I got it. Sorry. Sorry, that's my fault. I think I overcomplicated the situation.
So let D1 up to Dn to be the differences, and we just rank them according to the absolute value. Then we define W plus to be sum of ranks among all positive DI, and W minus to be sum of ranks among all negative DIs. Then we test the minimum of W plus versus W minus. Reject if this value is too small. So for example, I compute my D first. D is equal to Y minus X. Then I get 2, 6, 10, 12, 13, minus 3. Then I rank them according to absolute value of D. So this is my rank. And I sum up all the ranks for positive D, also sum up all the rank for negative D. Then this is my D plus, this is my D minus. Yeah.
Okay, so I have a questions. Maybe. So what if we confuse the dependent and independent Mann-Whitney test? What is going to happen?
In terms of T distribution independent of two
No, we just talk about the man-Whitney testing.
Man-Whitney test.
Yeah, I think that will be simpler for us to digest. So what if they're supposed to be paired? So if we misused the significant test, what is going to happen? And for this case,
because here for pair t-test, we are only comparing whether the difference, whether there's a difference for the same patient.
Yeah.
But for the independent case, we are testing the difference for any individual from group X versus any individual from group
Y.
Maybe
let's go through your examples, your last examples, your second examples in independent man-Whitney testing. So that is fine. So for this case, we can calculate the d-value, right? Suppose
if it is paired, then if we calculate, then it should be 1.
Or 1. So still fine, right? Still fine. And so this case will be too obvious. So maybe you can choose the next. No, I'm saying that it goes through the yeah. So maybe we can pair these two.
No. For pair t-test, we I'm
going to have a random pair. So what if I have some random pair here? So can we calculate the W soon? Oh no, I think that was not the case. So I can pair like this, right?
Because for paired test, the only requirement is for the same individual, after treatment, I get better or get worse. But for like independent case, I need every example in Y to be significantly better or worse than every example in X. So
I think that depends on how we pair, and they are supposed to have a pairwise combinations, which can.
So I think
into a significant
for
can turn into a significant group into insignificant, or can we? And if we're not specify how the pair looks like, we are supposed to have a pairing combination, which makes a significant result insignificant, right? So if we pair like this, and in Chinese phrase we call it 田忌赛马. So somehow we can have a comparisons to make 2 to pair with 11s, and then for every pairs we can make the red circle with the red circles, and then we will say that it's very likely we can say that Y is significantly better than X, and not vice versa. You get my point? Yeah. So that's the difference between the pairwise. So
I think man-Whitney test is just to look at all pairwise difference between two groups. But for paired t-test, we only look at one predetermined pairing.
Yeah, sure. Yeah. So if we get confused, we somehow it is possible that we may turn let me see. So here are the questions. So here let's come to questions. What if we misuse the independent man-Whitney U test as the dependent man-Whitney U test?
Misuse.
Yeah, misuse. So here, just for man-Whitney unit test, what if we use independent as dependent, and what is going to happen?
What is the ground truth?
The ground truth is independent.
Ground truth is independent.
And we use the independent. And there's a matching.
But why you misuse?
What if, I'm saying, what if we do this? And that matching or that manner matching combinations may give us some
misleading result.
misleading, but it can be better or it can be worse.
Yeah.
Either possibles, right? And what if we misuse the independent? Suppose we misuse the independent as dependent. So in this case, I think the harm of the latter is less than the harm of the former, right? So I'm not sure. Can you follow me? So if we make this case, I think we can still draw a reasonable, good conclusion.
But if we make this case, then maybe we will turn a significant value to insignificant value.
Yes.
Because we compare all the pairs, but actually we don't need to compare all the pairs. We just need to compare the corresponding pairs. So all the extra pairs can bring a disadvantages to the significance.
Yeah. I think we cannot. I think maybe the consequence of both misuse is severe. Could be in worst case.
For example, a patient before smoking, his blood clotting level is very large. Then if we randomly pair this individual with other kind of observation, then that will deteriorate our results. Yeah.
Okay.
So just a conclusion here. If we have independent two groups and we assume normal, then we can use two sample t-test. If we do not assume normal or we have outliers, then we can use Mann-Whitney. So Mann-Whitney is naturally robust to outlier because I only care the rank. I don't care the exact value. If I have paired two groups, then I can use pair sample t-test or sign rank test. So an extension is that if I have more than at least three groups, then the corresponding test is ANOVA and Kroska-Wallis.
Kroska-Wallis.
So this one is also some rank test. Okay.
So if n is larger than 2, so how do we say? Suppose we have three groups, A, B, C, and how do we supposed to have a ranking for these those three groups? Am I right?
Yeah, our test will be they're all equal. So.
Okay. So if it's not equal, so what if A and B are equal and B and C are not equal?
Then we still reject.
Okay.
So this is used when I have some categorical variable, and I have many factor levels for this categorical variable, and I want to test whether if my categorical variable takes different value, whether the distribution change or not.
Okay. So I know you prepared them, but I suggest we skip all those three groups difference, and you can share the slides here. If any students is interested to look into the Kroska-Wallis test or the group test, the significant test is more than two groups, and we can talk offline. And if necessary, we can organize another group meetings for presenting this additional content. So you did a very good job at the presentations. I think I would like to say that I set a good role model here. Thanks, Ruofan. So I think we do not rest, and we try, and we let Yihao to take over and give us the second presentation.
Okay.
Okay, so it's a NIPS 2019.
Yeah. Okay, shall I start?
Sure.
Okay. So hello everyone. Today I'm going to present the paper TreeCaps, tree structured capsule networks for program source code processing. It is presented on the 33rd Conference on Europe's in 2019. So the authors of this paper is from A-Star in Singapore and from SMU. So the first author is from A-Star, and the second author is received a PhD from SMU when the paper is published. And the third and fourth author is they are both associate professors at SMU.
They are all tenured professor.
Okay, so before we get into the paper, let's get some background of the topic that the paper discussed. First of all, I will introduce what is a convolutional neural network. So I guess you are all very familiar with the CNN. So the framework here is so the CNN is mainly used. One of the most common tasks is to classify the object in the pictures, and the one of the advantage of CNN is that it will extract some basic features from the input images in the first few convolutional layers, and then use the fully connected layers to classify the objects. But there are some drawbacks of CNN. So one of the drawbacks is that the max pooling layer will lose some valuable information about the input pictures. And the other one is that it doesn't account for spatial relation between different parts of input images. So for example, we take the example of a dog picture, and suppose the CNN has extracted the feature of eye, snout, and mouth of dog, and each channel of the convolution layer may only contain the specific feature, for example, the eye, the mouth, but it does not contain like the position of the eye in a face and the angle of the eye in a face. So when we have the drawback is that like we look at the picture on the left, we when we want to classify the abnormal face, the CNN will still output that the picture is a face with a high confidence, but we can see that the picture we want to classify is not a normal face. So that's the drawbacks of CNN. It will lose the spatial relation between different parts of the input images.
But I think somehow CNN has different layers of sliding windows, so
Yeah.
you somehow can still preserve, right? So of course, if we start with a sliding window of such an eye, we definitely will lose such a case. But if we have a larger sliding windows, and what is supposed to be? So if we have a larger sliding window, so we can have both eyes, including the sliding window. We may still preserve that information.
Yeah, but usually we don't have the sliding window is relatively small, right?
Sliding window, not sure. It depends on how we design the model architecture. If the model has the large sliding windows just going through the network, through the images, we can just
Yeah. But as long as the sliding window is not the whole image, then it loses the positional information of the window.
Okay.
Because the whole network doesn't record the positional information inside. Even if the sliding window is applied sequentially, but the sequence is not recorded. Okay, so to overcome this drawback of CNN.
Oh, sorry. So I think we need to have analytical discussions. Can you go back to the previous slide?
Okay.
So, previous slide. So still have previous slide. So, just getting through the animations. The next one. Okay. Yeah. So losing value information. Of course, the error losing information and spatial relation different parts. So what if we apply attention? So if we use attention, we can address the spatial relations of different parts, right?
If
So
we use
do you know we can use attention, the self-attention on TN, so we can measure the relation between different parts. For example, especially self-attention, and there's a lot of GAN, especially S-GAN, W-GAN, and C-GAN, will use self-attention to maintain the relation.
Yeah.
Of between, and so that's supposed to not be a very so why capsule? Why TreeCapsule? So I think self-attention can also address this problem.
Yeah, but self-attention is addressing the problem within the layer. But the capsule will also establish the relation between the layers.
So I think this is very good architecture. I think just of course Ruofan have the same tricks. So when we're talking about the problems, when we're talking about the technique, we always start the problems, and what specific problems are we going to solve, and why existing approach cannot address this problem. I think this is a very good skeleton. But so with such a clear structures, the people can raise criticism on that, right? So for now, I just raised the criticism that these problem definitions, I'm going to say the paper, maybe it's just your problem or presentation. So given such a problems, there existing approach like self-attention. But if I'm the reviewer to go through this paper, my first question is that why the self-attention cannot be not used to address this problem. And it will be either the case that self-attention will be a strong baseline as a tree capsule, or maybe the problem presentation can be further improved. Okay, can keep going on.
Okay. So the self-attention is addressing like the different features, the relations between different features in the same layer, like the right eye and left eye, what's the relation between them, but it's not addressing like the eye with respect to the face. So the face is the feature of the next.
Also portable, so it can capture the relation between maybe the right eye with the nose, the relation between the right eye with the mouth.
Yeah.
And it can also capture a lot of the pixel relation that I think it was supposed to be. And because self-attention is an n by n matrix, it will capture the relation between every feature map. Every feature map will be captured.
Yeah.
So that it's very hard to give an argument here.
Okay.
So I'm not sure whether they provide a baseline. If not, maybe that will be a question.
Okay. They didn't provide the baseline with the attention. Okay, so to overcome this problem, Geoffrey Hinton has proposed a capsule network at NIPS 2017 by the paper Dynamic Routing Between Capsules. Geoffrey Hinton is regarded one of the founder of deep learning, and he was awarded Turing Award in 2018. And the formal definition of capsule is that a capsule is a group of neurons whose activity vector represents the instantiation parameters of a specific type of entity, such as an object or an object part. And the length of the vector is to represent the probability that the entity exists, and its orientation to represent the instantiation parameters. Maybe this formal definition is quite hard to understand, so let's use some examples to understand it intuitively. We can regard the capsules as a vector, specifying the features of an object and its likelihood. So we can, let's look at the picture on the bottom left. So this is a normal neural network, and suppose the feature 5 is already extracted, and the neuron has output the probability of 0.9, 0.8, and 0.4 for input for different input images. And then we look at the picture at the right. So here we use the capsule, and we use the vector of size 2. So the length of the vector represents the probability of the specific feature, the specific picture being 5. And the angle of the vector represents the features of the picture, and those features can be any pose, like the position, size, orientation, deformation, velocity, etc.
Capsules are a vector specifying the features of the object and its likelihood. The feature can be position, size, orientation, deformation, velocity. So how can it be present the deformation velocity?
And
this are those features specific or are deliberately specific?
It's not deliberately designed. It's supposed to be learned.
And also you mentioned the length supposed to be the confidence, so I didn't get this point. And can you use a few words or sentence to specifically and briefly, concisely, and tell us the difference between the capsules and a normal neuron?
So the input and output of a normal neuron is scalar, and the input and output of a capsule is a vector. Yeah, and the output of the vector is designed such that the length of the vector represents the likelihood of the feature exists, and the orientation of the vector represents different features.
So sorry, I still so for neurons and for layers, the input and the output between the layers are also vectors, right? The neural layers are also output. And it seems that the capsule can output a dynamic, a vector of dynamic size or a flexible size.
The size is fixed.
The size is fixed.
Yeah.
Okay. So how is the difference between the capsule and a neural layer?
We are talking about the specific neuron, but not the neuron layer.
So is that possible to replace the capsule with a neural layer?
Replace the capsule with a
With a neural
layer.
layer, because the neural layers, it seems to me that almost have the same capability of representing the information, right? So the output is about the length, output about angle, deformation, velocities. Why a neural layer cannot achieve this? Why we have to use the capsule?
Because we want specific properties to be preserved when the capsule get an input vector and output the vector. There are some operations inside the capsule so that some properties are preserved, but the neural layer
it's more like a cell in LSTM, something like that, right?
Yeah.
So it's a specifically preserved the cell, or it becomes it's called a capsule, and these capsules are going to extract it. Somehow it's like embedding our domain knowledges into it.
Yeah, kind of. Okay, so I continue. So what does the capsule do? Let's first look at a normal neural here. So for a normal neural network, we first the input of the neuron is scalars, like x1, x2, x3. They are all scalars, and then we calculate the weighted sum of the scalars by multiplying x1 with w1, etc. And then we apply the nonlinear activation function to the summation to get a scalar output. So this is for the normal neural network. But for capsule, we there are some differences. The first is that the input is a vector from each capsule for each capsule, and the input is a vector. This is the first difference, and the second difference is that for each input vector, we multiply it with a matrix. We call it transformation matrix, and this matrix is supposed to contain the spatial informations, the spatial relationships between different parts of the input. And after the affine transformation, after the matrix multiplication, we get a predictive precision of the of the next layer's feature. So, for example, suppose the current layer is we already extracted the dog's eye, the left eye, right eye, nose, and mouth. And then after the matrix multiplication, we get a predicted face for each input vector. So at the later stage, we use this predicted face to calculate whether those predicted faces are correlated or interferes with each other.
I didn't get that point. So can you be specific? So your this slice is the logic of your this slice going to about what a capture do. So giving these captures, we have a left eye, right eye, nose, mouth. So suppose given a sliding window looks like this, and it's going to output 0.8, 0.9. So what does really means?
So the length of the vector here is the probability of existence of the eye. So that means by
the way, so here, what it captures, of course, from the human perspective, it is an eye, no problem. Yeah. But what if it is classification problem, right? It is supposed
Yeah,
to
yeah.
be in classification problems.
Yes.
So when we have an idea, so when it's going to extract the features, is there any classification for a specific feature map or a specific sliding window?
There's no classification.
Yeah, there's no classification. So I really cannot get it. So this is 0.8. What does this semantics? What the semantics really means?
Yeah. So the left eye, the vector is 0.8 minus 0.5 and 0.7, right?
Yeah.
So
So why these numbers? Why these numbers matters? And what is the meanings of that matters? I didn't get it.
so this vector, so for normal neural network, here is just a number, but for Capsule, here is a vector, and this vector is supposed to represent the features, different features of the of this part.
So Capsule is actually a neuron. It's kind of neurons which can output to a multiple value.
Yeah.
And this value actually means very different semantics.
Yeah.
And there's a feature called a lens. And the lens, you mean the confidence. And can I ask what is the confidence about?
They interpret it as confidence, actually. Because
so understand the number will be the angle of the eye or something else like that.
yeah.
So the benefits, I'm asking the benefit because the network is going to learn the feature in an automatic way, right?
Yeah.
So for the neurons, it's taking a lot of input, just as Yihao said, a vector of input, a numeric vectors and synthesize another signals or output. And here it output three. It have three outputs, or 4 or 5, whatever it is. So what's the benefit of such a structured design? I didn't see it. I haven't seen the benefits.
Because the output is a vector, so it can contain more information.
Maybe the origin output maybe a feature, maybe another picture. That means the origin is from the parameter to a picture. Now it is from picture to extract some parameters, extract some important information.
Yeah, I think the normal neuron can also do the same. And I'm keeping asking is the difference. For what I understand now, is that it will have a different number output, and for each capsule, maybe there's a difference in the internal structures. But I haven't got it why it can bring additional benefits, or why it can do something and achieve the effects of the self-attention to capture the global features. Why? I'm always keep asking these questions.
Because for normal neural network, here is only a number, maybe 0.8. It's only a number. So here the number can only represent that maybe the likelihood of this I.
Yeah, only the confidence of this.
Yeah, only the likelihood. But now we use a vector, and this vector can not only represent the likelihood, but also represent other features of this eye, like the angle of the eye, or the color of the eye, like something like that.
But why normal CNN cannot achieve this? We have a lot of filter, right? So each filter, a filter is more like different filter is more like a different sliding windows, but of the same size. It keeps scanning the images, and we can still scan it with when increasing the number of filters. Why can't we achieve this? Right, the first filter capture 0.8, the next filter capture minus 0.05, and the third one takes capture 0.7. The information is just here.
Yeah, but they are not grouped together.
Do they need to be grouped together? So why we have to group them together?
Because we want to, because the feature is treated as an entity, and the properties of the entities should be grouped together to make the calculation consistent. This is my understanding.
Okay, let's keep going on. Let's keep going on. But I think we have more detailed understanding. This is the paper of Hinton after all. So there's supposed to be something there. Let's keep going on.
Okay. So after we do the affine transformation, then we just do the weighted sum of the input vectors. And here, in the paper, they use a technique called the dynamic routing. So here means that we still take this picture as the example. So after we get different predictions of the phase, then we use dot product to see whether those vectors are similar to each other. If they are similar enough, that means that they are corresponding to the same part. So the coefficient, the coefficient C1, C2, C3 here will be have larger weight. If the predicted phase here is not similar with each other, then the corresponding coefficient here it will have less weight. And this is the idea of dynamic routing.
Cij are co-coupling coefficients. So anyone familiar with the dynamic routings here? You familiar with that? Hello, Yufan. Is there Yufan here?
I just read some material of the capsule network. I think I can understand by the word embedding. You can just thought that originally we input a word embedding, and every dimension of the embedding is the input. Now we see the word embedding as a whole input and a whole input to one neuron. That means it is vector in and vector out. Before it is scalar in and scalar out.
Yeah, I got it. So I'm more asking is that I think Yihao has clearly defined the input and output on the capture. So of course it's very good that it interpreted as a embedding approach. So but I'm asking about dynamic routing algorithms. So what's the purpose of dynamic routings? So you can see Yihao, when you are saying this, we have a lot of puzzling here. You're actually of course, the goal of presenting is that spend time on understanding details and presenting in a vivid way so that you can share information for us in a very convenient way. So we don't need to read the papers. But when you read the papers, we have so many questions here. So can you, using very concise way to further give an example, providing example of dynamic routing?
Yeah. So here,
why they call it dynamic? Why they call it routing?
Okay, let me draw some graph. So suppose this is the the first one, the first capsule is the eye, and this is the like leg. So this one is eye. This one is leg. And for the next layer, the first capsule represents the face. And the second capsule represents body. So, so the coupling coefficient here is meant to adjust different weights for the current layer's features contributes to the next layer's features. Like
so would prone some kind of the weight? Would prone it?
The
prone, prone means reduce or minimize the weights in between.
Yeah, the weight is adjusted during training using the dynamic routing. The dynamic routing is
but the dynamic routing isn't a feature for a normal network. So suppose unless these features, unless these of your features has been specifically can be determined as space, and somehow the routing going to happens. Otherwise, if we consider just a capsule, normal capsule or normal neurons, and the neural network can do this by its own. Right? We can do this by its own. There is no need to say this is dynamic routing.
Yeah, but they designed the specific dynamic routing during the training. During the training process, to manually adjust the weight here, adjust the weight of C1, C2, C3. So this weight is adjusted in every training steps.
Okay.
So in each training step, the dynamic routing algorithm is applied once.
So it means the backpropagation.
Yeah.
So what I mean is that the backpropagations can have the effect of dynamic routing on its own. There's no need to do this. Right.
Yes.
So why we need to explicitly say that there's dynamic routing?
Because I guess the reason is that they want to explicitly control the weight here.
So, okay, maybe Yifan, can you share, maybe you can switch to Yifan share pictures in our group. Maybe Yifan, you can switch, maybe you can switch to Yifan's screen and you can share that and explain it.
Sorry, actually I just find the picture. Maybe will help Yihao, but I actually do not understand
how to interpret this, right? Yeah, so maybe let me share my screens. And I think it's kind of important to share to get it to understand this well. I think all of you can see my screen, right? Yeah, so here I think Yihao, I don't want to say that, but I think that you failed to clearly address my confusions. If you cannot address my confusions, I suppose that is confusion of all of us. Then the goal of presentations does not take so many effects. It's not so effective. So suppose each U is supposed to be capsule, right? Am I right?
It's a vector, yeah.
It's a vector, and a vector, and after we apply some weights, it becomes a hat. Vector output of a nose capsule that encodes existing and opposed. So it's output of capsule, and the way matrix can encaps the special relation between nose and face. And why these three can capture the nose and the face? And
Because the next layer is face.
the next layer is face.
Oh, because the output is face capsule, so we will learn
Okay.
this weight matrix. Yeah.
Okay, but how we can use this U hat layer as a face matrix of low layer. No, the matrix multiplied the output of a low level nose capsule. So this is still nose, right? This nose and nose. And how this can represent the relation between nose and face.
It will be learned. It will be learned.
And how do we know it was actually designed to learn the nose and the relation between nose and face?
Because the final UJ is the face.
Oh.
The final UJ.
Final, the last one.
The last one is face.
Yeah.
Okay.
Yeah.
But how do we know? How do we let this capsule to be the face capsule?
So this neural network is from the part of the small part of face to a whole face, from nose, from eyes, from ears, then to a whole face, maybe like this.
I think it's trying to explain. So, but in practice, we don't know what kind of feature each capsule represents.
I agree.
Oh.
Okay. So Yihao, can you also answer how the scratch formula looks like?
Yeah. It's in my next slide.
Okay, I will let you share. Please share your screen share. Please share your screen.
Okay. So in the scratching function, the scratching function is looking like this. Is comprised of two parts: the scratching part and the unit scaling part. So the unit scaling part is to preserve the vector orientation, and the scratching part is to resize to make the vector size between 0 and 1. And S here is the summation of the weighted summation of U1 hat, U2 hat, and U3 hat.
The control. So each scratch will output a scalar.
A vector.
Still, why it is vector?
Because S is a vector.
Okay. So S is a vector. Each dimension of C. Right. S is actually the summation of each dimension of C. They combine together. Okay, please go on.
Okay. So to take an overview, the capsule network, look at this. First, we will still use the convolutional network, convolutional layer to extract the basic features. And after that, we apply the capsule layers to the extracted features. And at last, we will calculate the different the class probabilities using the L2 norm.
Okay, keep going on.
Yeah, so this is the background for the capsule network, and the approach here, the approach in the paper presents a very similar flow to the capsule network, with some adaptations to accommodate the unique properties of source code. So the overall workflow is showing in the picture. Suppose we have source code as input, and the first step is to vectorize the source code. And after the vectorization, we apply 3 capsule layers, naming as the primary variable capsule layer, primary static capsule layer, and co-caps layers. And after that, it will output the probability of classification after the softmax layer. So next, I will detailedly introduce what's going on in each layer. So the first step is to do the AST vectorization. The paper uses the AST to train the embedding for node types by applying embedding techniques similar to word-to-vec. So after we learn the vocabulary of the AST, then we can use those vocabulary to vectorize the AST.
For each AST node, we have an embedding, right?
Yeah,
for
each individual
node. Not a
node.
word to vector, it's a node to vector.
Yeah, but the technique is similar to word-to-vec.
And how do they train the embedding network?
They only mention one sentence. They didn't explain. Yeah.
Okay, but it's
this is not the
easy.
focus.
So
Yeah.
as long as we can design a few classification problems for the code, we are somehow able to classify the semantics of each AST node. But usually the AST node somehow, I'm not quite sure, but AST nodes somehow have limited semantics compared to the control flow graph and the program dependency graph.
Yeah. So after this step, we get the vectorization, the embedding for each node in the AST. And the next step is the next is the primary variable TreeCaps layer, and it will get the input from the vectorized AST and output to the primary static capsules. So in this step, the first part is to apply a convolutional window of depth D on the AST tree. Suppose the part of a tree with depth D has k plus 1 nodes, then we compute y as the following formulas. Here, the eta represents the positional and depth information of the nodes. So in particular, D is the depth of node, and P is the position of node, and K is the number of nodes siblings.
Now, can you note that the T, there's a notation of the TLR, or can you annotate something? Put some notations here.
Yeah. So here D and DI represents the depth of node, and the PI is the position of node I, and K is the number of node siblings. So based on this formula, we calculate eta T, eta R, and eta L, and then we substitute into this the overall formula to get the Y, the output Y.
And the output of WT L, and what is LTLR means?
LTLR, where is LTL?
TLR is supposed to be the depth positions, and number of siblings, and also the same. So it's more like so for the AST embeddings, it actually for the capsules, the output of each capsule has only 3 dimensions. Am I correct? Or
no, this is not the output of capsule. This is
I mean the TLR is an output of the capsule. Is that correct or it's not?
no. The TLR here, TRL is just three different ways to be applied on the X. X is the vectorized
AST node.
Yeah.
A vectorized AST node.
Yeah.
And so the network structure is hardly embedded or hardly encoded with regarding to depths, positions, and number of siblings.
Yeah. So this is the first step to in the primary variable TreeCaps layer, we compute this Y. So after we get this Y, the next step is to use because here we only here is the process of apply a one convolutional window. So we use epsilon such slices, such convolutional slices with different random initializations for WB. This is similar to CNN for image data. And then we group the convolutional slices together to form n sets of capsules with output U. So here n, how to calculate n, we use T. T is the tree size, and V prime is the dimension of the convolutional output vector, and epsilon is the number of convolutional windows, and D is the dimension of capsule vector. So that means we apply the we apply different convolutional windows on this tree, and we group the output to calculate the Y, and we grouped all the Y together and divide it into capsules. This is what this step means. And after we divide it into n sets of capsules, we apply the nonlinear scratch function to make it to make the vector size into between 0 and 1. So this is what the primary variable TreeCaps layer do, and why the name is called the variable TreeCaps layer, because the size of the tree, the AST tree is will vary from examples to examples. And so the capsule in this layer, the number of capsules in this layer will also vary. Yeah, so we need to find a way to fix the number of capsules before we go into the next step. So this is the algorithm called the variable to static capsule routing. So in this algorithm, we first initialize the output of this layer by the largest A, the highest L2 norms in the PVC layer. PVC is the primary variable capsule layer, the last layer we introduced. So the first is to sort the output of the PVC layer according to the L2 norm. And then we pick the largest A vectors and fix this A to so that we can convert the variable
here,
to
Yihao.
static.
So I
Yeah.
think I have to stop you here. So I think if I keep you going on, I think not only me, but also the rest of students will getting more and more puzzles. But so is there anyone who have the questions here? So I'm afraid when you keep going on, even I may stop the questions. So can you go through a few slides? So I have a few questions for you to address. I think start a question. No, not go back to go
Okay.
next. Let me go through a few points. So you have 27, right? You can go through that. Like next one, the next one. And that becomes results.
Yes.
So the results, okay. So let's skip the approach. I have a few points for you to ask about approach. You can quickly finish the experiment results, and I'm going to let's have a quick discussions on the technique.
Okay. So this technique, the paper used this proposed method to do the experiment on the program classification. And
how and what kind of classes a program can be? What kind of classes categories? The sorting algorithms.
Yeah, sorting algorithms.
So how many sorting algorithms can be used? And they're supposed to training, right? They're supposed to training set and testing set.
Yeah.
And they're supposed to collect a large number of sorting algorithms of 346 trainings. Is that enough for a deep neural network model? 300. Sounds like kidding.
Yeah, that's the statistics.
And they published on AAAI. So no reviewer mentioned these. Have you checked their open review?
No.
See, Xiangling. So given a AAAI paper, there are so many drawbacks there. So given a deep learning model, so if I were the reviewers, I'd probably not accept it, given the amount of time. It's not convincing. Okay, keep going on.
Yeah. So we can see that for data set with large number of classes, the performance will drop. This is in accordance with
by the way, so
the
how
capsule network.
is 104 classes? And what is that 104 classes?
I didn't investigate the data set.
Going on.
Yeah, so they also did the model analysis on the method, and they have experimented with different capsule vector size with 4, 8, 12, and also they have add an extra capsule layer, and we can see the performance will increase if we add an extra layer, but will not increase much. And last is the limitation of the paper. So for this method, because it inherits the features of capsule networks, and also the drawback of the capsule network is that it has high computational complexity.
Okay, so let's get rid of the limitation. So let's go back to the technical details. Maybe we can leave a no, we do not go back there. So those kind of algorithms can be used for. So can you open another white page, a blank page? Yeah. Okay. So can you list here a few points? So we should have a thinking structure here. So we now have it's called the tree capsule, right? The tree capsule, something like this. So from my point of view, compared to the existing transformer or LSTM structures, the tree capture is supposed to provide more informations or to extract from the code. And the code representation, anyway, if we're going to pass in the code will somehow represent in different form. Someone using AST, someone use dependency graph, and someone using text per se. So in this approach, it's just look into AST node, right? So anyway, any architecture was supposed to have an intention. We're supposed to have intention of what additional architecture or what additional information the network going to extract compared to the other model. For example, for CNN, it's going to extract the feature of the local features, right? You can keep looking the local features and looking to the local invariants of the images. And also for the transformers, is trying to capture the relations between each word, right? For transformer, it will have using attention. They have a multi-headed attention to capture the different relation between the tokens. So that's the idea of a transformer. So would you please give a concise point? So what does what information these tree capsule can additionally extract from the AST comparing to existing model architecture? So maybe I leave a code like int a equals b, and we call a method o called b, something like this. We have a code looks like this, right? And they will be translating tree. And what features existing model cannot capture. However, the tree capture can be additionally captured. Of course, we have already know that the tree capture, when given one capsules, we feed a node there, and it will output a few features of nodes, right? A few feature of nodes. And what additional information can you annotate on these slides and give us the big picture? So all those algorithms are, of course, they are important, but they are all details. And what we discuss is looking to the rationale. And also, if you can also answer whether these tree captures will be used in our project, that will be excellent.
Okay. First of all, I don't think this can be used in our project because this is specifically for classification tasks. And so the advantage of this method, one of the advantages that it tries to include the relationship between different capsules. So we can think of capsule as a extracted feature of a certain part of the program, and
but
it's quite similar to attention.
But the capture, the input, the output of the capture could serve as the input of another capture, right?
Yes.
And so after multiple layers, and what does captures can contribute to capture information in the code?
After several layers, then it will represent the high-level features of the whole code, of the whole input source code.
And also, I think we should quickly call it a day soon. For my last question for you is that for each node there will have a label. For example, this is supposed to be equal, and this is supposed to be, and this is supposed to be a declaration, and this is supposed to be int and a, right? This is what an AST looks like. And how those labels means, and what if the variable names, how these variable names serves as here. Anyway, we're classifying the sorting algorithm, right? We're classifying the sorting algorithms, and what do you think? What if I change the quicksort name of quicksort into a bubble sorting, into bubble sort, or you use a merge sort? So will this label affect the classification result? What do you think?
I don't think it will affect much because it is extracting features, but not the name. Name might be only one feature, but yeah, but I don't think the capsule network will put much weight on this name feature.
I don't think so. I think, but anyway, so there will be supposed to be arguments. So I suggested, I think your presentation didn't address a lot of my questions. And personally, I still have some confusions here. So I would like to ask you to further go through the papers and also some other interested students like like Ruofan. You can also investigating this paper again. So I'm going to say that maybe it's a problem of presentation, but also I think this paper will have some fundamental problems to address, and whether tree capture can really help these problems can really help, and what additional information can keep the tree capture capsule to preserve or extract, they're still kind of at least we haven't addressed these problems. So for Yihao, would you please reinvest and revisit this paper and give us some information to answer two questions. The first question is comparing to existing models, like there's the GN model, the graphic neural network models, whether what additional information can keep the tree capsule extract and preserve? This is the first question. And the second question is how, and how the model architectures can preserve and capture such additional information. If you cannot get answer from the papers, you can send the emails. And also, if possible, so I have the WeChat account with one of the authors. I can answer for you, but I think from a more formal perspective, we need to investigate it first. And would you please send me share the information to me or in the group as well by the end of week, by the end of this weekend. That means by tomorrow night.
Okay.
Okay. So the question supposed to be clear, right? The first is that what additional information of the code can tree capsule architecture can extract it and preserve? And the third question is just why. Okay.
Okay.
Okay. So
yeah.
So I think I assume that you spend 1 or 2 days to prepare the paper, but this paper might need more time to digest. And also I suggest that when we are present the paper, I think it's an excellent chance for us to digest, discuss, and also to improve your presenting skill. You can look at Ruofan's presentations. He gives very vivid examples. And I'm not saying you are not good. You are good. And you're also reliable implementing a lot of experiments and our ideas. So yes, you're good. But when you are providing the algorithms, especially the pseudocode, a good presentation will not put a pseudocode on the slides. So that is the worst to present a pseudocode. So when we're talking about the paper presentations, we do not need to be very accurate. If the people would like to be very, very accurate, for example, the tree capture seems to be an excellent approach in our research project or our next paper. We definitely need to investigate every detail of the tree capture for you and I or other collaborators. Definitely we need to do that, but not on these discussions. In these discussions, you are going to show a high-level picture of how the approach can work. But unfortunately, it seems that we miss, at least for me, I still miss such important information. I still cannot capture the rationale And all we know is that a tree capture is a fancy architecture provided by a big name. And how it will be useful in this specific task, still something missing. So when I suggest that when we have a pseudocode, we use animation, we use examples. So we remove every line of code, and all we use for present pseudocode is just animation. And your animation is not necessary, does not necessary to capture every corner case of the pseudocode. That is not possible. Otherwise, it will be stupid and tedious. You just show the animations of the major workflow or program flow of the pseudocode, and that is all, right? So we need a way to interpret the code into an animation. So in the process of doing this, you are improving your presentation skill. In the meantime, all the audience can benefit from your work. Otherwise, they will spend more time to digest the pseudocode. So that's a win-win situation here. But you just pick, but when within very limited time slot, for example, only prepare 1 or 2 days, maybe only 1 day to prepare the papers, you have a problem. You may have the problem to digest every aspect of the paper, let alone to leave some time to give a very good presentation. So that becomes a problem.
Yeah.
Okay. So
yeah, I want to argue that actually this paper, because it involves a lot of information. First of all, it involves the capture network. So I have spent like 10 plus hours to understand many details of the paper, and also the corresponding terminologies and the background knowledge. So, but maybe my presentation skill is not good, because I want to show the details I have understand, but maybe because it also takes me several hours to understand. So maybe here it's quite hard to
and also understand
make
the
you
paper
understand in
might be
1
involve
hour.
a lot of complicated concepts. To digest those concepts one by one is no easy job. I understand that. And also, I suggest that you go through the paper reading skills. So it is not necessary to read every word. All of us know that it's not necessary to read every word of the paper. And especially when I serve the reviewer, I need to have maybe 10 paper to review within a few days. If I cannot read the paper quickly, so the research community service will occupy a lot of my time. So reading every word is not a smart strategy. So there is a specific paper called How to Read a Paper. I think I shared it in our group. I will share it again. And how to read a paper quickly. So when we are preparing a presentations, we extract the most important rationale and information. You can see for a lot of the paper presentations, it only allows the authors or the presenters to give 10 to 20 minutes of talk. So in our discussion, in our paper discussion, in our group, in our meetings, we can take a lot of hours, say 2 or 3 hours. But for the paper presentations, it can leave only 10 to 20 minutes. So the audience have to provide the most salient, the most rationale information, and that's all need for paper presentations. If we go details, and that's fine. So in this, my point is that it may not necessary to understand every details. We only need to understand the details supporting the rationale, almost relevant to the rationale and the big picture of this paper. So that will be all what we need for presentation. Yeah. I think one of the example, I think Wang Chao is not here, but I'm going to say one of the very good examples is Wang Chao. And Wang Chao is an FYP student who has a GPA of 5.0. So that means as far until now, he haven't got a class grading less than A. So anyway, so every people have limited time and energy. How does one can achieve such a good grade? I think there's always trick there. Of course, students can be smart, but when observing his presentation, I bet and dare to say that Wang Chang definitely do not consume every word, but his performance or the paper representation skill, you can see compared to Ruofan and Xiangling's slides. So those, you can say their slides kind of delegate. They prepare and spend a lot of time. And Wang Chang's slides somehow a bit rough. But his strength is that he precisely pick up the most important point to represent. I understand that maybe he only read 30 or 70% of paper, but as long as the big picture is there, that'll be fine. That'll be fine, and there's no point to argue. There's no point to argue, and all his logics are very complete. As long as he presents a complete logic, there almost no question to attack, right? So maybe that also, I'm not saying that you can just reduce the efforts, you just to be lazy too much, but the idea is that big picture and pinpoint what's the most relevant and the most interesting information. That may be another skill for you to improve.
Okay.
Okay. I think these meetings have taken too long, and thanks for everyone to attend it. And I assume there's no more questions here. Let's call it a day. And thanks to all the presenters. Let's meet next week. Bye.
Bye.